This is the Millau Viaduct, the tallest bridge in the world. Its highest tower stretches a staggering 343 meters. So high, the bridge glides above the clouds. But this is a megastructure they said couldn't be built.
When I've shown first the drawing of this bridge, they really thought I was crazy.
The team attempting to build this amazing freeway in the sky had to survive landslides, fight winds gusting at 130 kilometers an hour, and weather massive storms as the bridge simply hung in the balance. It's a bridge that pushes the boundaries of engineering to the limits, and then beyond. Imagine building a series of Eiffel Towers, then slinging a 4-lane highway between them, all the way across one of the deepest valleys in France. Impossible though it sounds, that pretty much describes the building of the Millau Viaduct. From the start, the construction team faced 3 daunting challenges. 1. Build the tallest bridge piers in the world. 2. Put a 36,000-ton freeway on top of them. And 3. Erect 7 steel pylons, each weighing 700 tons. And what's more, they had to do this hundreds of meters above solid ground. So high that if you were on top of the Eiffel Tower, you'd still be looking up at this awesome bridge. October 2001, the team break ground. They're required to build a bridge that'll last for 120 years. And to win the contract, the teams promised to build it in record time, less than 4 years. By comparison, the world's longest suspension bridge, the Akashi Kaikyo in Japan, took a full 10 years to build. To up the ante, any delay will cost them $30,000 a day in penalties. There are 7 piers that are numbered from the northern end of the valley. Number 1 will pose problems because of the steep slope. Number 2 will be the biggest challenge since it's the tallest. Crossing the river, number 3 is not much shorter. Then 4, 5, 6, and 7 climb the gentler slope to the south. To begin, the team had to bury the foundations deep in the bedrock in order to support the enormous weight the bridge will place on them. But the forces of nature were stacked against them. Geologists have warned of the risks posed by the region's fractured limestone. The rock is full of cavities that are essential to the local cheese economy. These cave systems, close to Millau, are home to a unique bacteria responsible for the blue mold in the world-famous Roquefort cheese. But what's perfect for cheese could be disastrous for a megastructure. The geologist's diagnosis spelt one thing: landslides. This kind of catastrophe could jeopardize the entire project. Despite the warnings, building went ahead as planned. Then, well into construction, as predicted, a dramatic storm causes a landslide. 4,000 cubic meters of rock collapse around Pier 1. Fortunately, the fallen rock doesn't damage the pier, but the warning is clear. They're forced to divert precious manpower and equipment to stabilize the slope and prevent a repeat collapse. So if the area is prone to landslides, why did they build the world's tallest bridge here in the first place? The answer is simple. In the 1980s, France built a freeway linking Paris directly with Spain. This major artery headed south across the French countryside, while from the Mediterranean, the freeway headed north, until they both hit one of the deepest valleys in France and stopped dead. Welcome to Millau, France's least favorite bottleneck. The town of Millau is in the mountainous region of the Massif Central, one of the most tranquil parts of France. But in summer, this poor medieval town suffered traffic hell. The locals couldn't take it anymore. Neither could their mayor.
It was terrible for our reputation. When you hear every day on the television and radio, avoid Millau, there's a traffic backup, a 5-hour wait in Millau.
And it's not just the people of Millau. Two drivers, Jamila and Jemima, crossing the 30-odd kilometers between the freeway on either side of Millau, reveal exactly why this bridge is needed. Jamila, in car 33, will cross the new bridge, while in car 22, Jemima will take the old road across the valley floor. Getting straight on the freeway, car 33 approaches the Millau Bridge after just 18 minutes. The only delay is the 30 seconds it takes to get through the toll booth. Then driving at 100 kilometers an hour over the spectacular bridge, she takes just 32 minutes to get to the other side. Car 22, meanwhile, is just beginning the crawl through the medieval streets of Millau. Cyclists, pedestrians, people with dogs all need to be negotiated. Car 22 then has the long haul up the other side of the valley. The final timing is a staggering 1 hour and 35 minutes. Over an hour longer than Jamila, who took the freeway and bridge. It's clear exactly why the bridge was needed, but it took the French government a very long time to get round to building it. 12 years before construction began up in Paris, the Ministry of Transport first came up with a plan. Their head bridge builder, Michel Villageux, is no ordinary engineer. He's a man who thinks big, very big. Like the Normandy Bridge in northern France, the longest cable-stayed span in the world. With this record-breaking structure completed, Villageux was on to his next, Millau. His plan, another cable-stay bridge, but pushing the technology beyond anything previously attempted, with piers 4 times higher than the Normandy Bridge. The Millau Bridge would not only be the world's tallest, it would be unlike any bridge ever constructed.
When I've shown first the drawing of this bridge to the convenient authorities, they really thought I was crazy.
Villageux's Normandy Bridge has 2 sets of cables supporting the deck. But he wanted to up the stakes for Millau by losing 1 row of cables, so the remaining line would be forced to do twice the work. More dramatically, the 2.5-kilometer Millau Bridge, instead of having a single main span, needed a whole series of piers to support it across the valley. No bridge builders had ever attempted a multiple-span, single-line cable-stay bridge on this scale before. The French authorities had a problem. Nervous about Villageux's groundbreaking scheme, they held a competition inviting other engineers and architects to compete with different designs. The winner, Lord Norman Foster, is one of the world's superstar architects. In Hong Kong, he built the world's largest airport terminal. In Barcelona, officers literally hang from a mast on his communications tower. This is a man who regularly contemplates the impossible and delivers.
You know, it's the challenges, and it's one challenge on top of another, on top of another.
And with Malau, one of the biggest challenges was making it fit into the landscape, given it's just down the road from the famous Gorge du Tarn, France's equivalent of the Grand Canyon.
How do you make something which has to be so immensely strong against the forces of nature look very gentle, very delicate? How do you weave something on that scale into the most unbelievable landscape?
Ironically, Foster's answer was to take Villageux's pioneering scheme, then push it one stage further. He turned an elegant piece of engineering into a delicate work of art by boldly cutting out 2 of the 9 original piers and seriously slimming down the remaining piers and road deck. Foster wanted the bridge to appear as delicate as a butterfly, but this butterfly has to support the weight of 5 Eiffel Towers in gale-force winds hundreds of meters above the River Tarn. Getting the design wrong would be a disaster. Then, with Malau still on the drawing board, Foster's record as a bridge builder suffered a major setback. His Millennium Bridge in London is actually another record-breaking structure, the lowest profile suspension bridge in the world. But when this footbridge opened to the public in June 2000, it was a public relations disaster. Crowds walking over it set up a resonant frequency, and the bridge began to sway. As people adjusted their step to the small initial wobble, the effect was magnified. Though it didn't threaten the structure, the swinging motion became so dramatic, the authorities closed the bridge for a refit that took 1.5 years and ended up costing over $8 million. It was a bad omen for the Malau Bridge, where construction was soon to begin. And at 15 times the height, a design flaw would be a catastrophe. December 2001, France's Malau Viaduct, the tallest bridge in the world, is under construction. Everything about this project is supersized. It'll need 200,000 tons of concrete, so much that the team have to build a concrete factory on site. But there's nothing straightforward about this concrete. The formula must be just right. It needs structural strength to support the massive loads it'll have to bear. But it can't set too quickly, as it has to be hoisted into position and poured hundreds of meters in the air. And it needs to be just the right color to suit Norman Foster's vision. In fact, the architect's vision has created a headache for the construction team. He's designed each pier as a complicated geometric shape, tapering the entire way up with vertical grooves set into them to create shadows. But what's just a line on paper for the architect was a major challenge to build. The enormous piers are built step by step by pouring concrete into a temporary mold. To give the required strength, the molds are filled with a frame of steel reinforcing bars. In total, 16,000 tons of these steel bars are hoisted into place and secured. Laid end to end, they'd stretch the 4,000 kilometers from Malau all the way to Central Africa. The shape of each pier is seriously complicated. As a result, each time they remove the sections of red steel shuttering, they have to change the shape of the mold to fit the profile of the next 4-meter section. Manhandling these steel panels, weighing up to 15 tons apiece, is no picnic. And with the combined height of the 7 piers totaling well over 1 kilometer, they have to change the shape of the mold over 250 times. Every 3 days, each team on each pier went through this whole cycle. Then they repeated the process. But it was a race against time, with a permanent threat of delay. Keeping the entire build on time and to budget was the daunting responsibility of one man, Jean-Pierre Martin.
If instead of 3 days we took 4, imagine that multiplied by the number of castings. We'd end up with a 3 or 6 month delay.
With a penalty of nearly $1 million a month, this isn't something Martin wanted to contemplate. And this schedule wasn't his only headache. You have to be pinpoint accurate when you're building the tallest bridge piers in the world. Get it wrong, and the bridge simply won't fit together. Just 10 centimeters out, about a hand's width on each 4-meter section, and the tallest pier could be 6 meters off at the top, the width of a jumbo jet fuselage. Each team was aiming for a specific point in the sky. For Pier 2, this was exactly 245 meters above the ground, 546 meters from the north side, and 1,914 meters from the southern end. There was no room for error. The only chance they had to get it right was with GPS, accurate to within 4 millimeters. Using signals from multiple satellites, the team could pinpoint their position and make sure they're on target for that critical point in the sky they needed to hit. Month after month, the piers climbed higher. Finally, by November 2003, they reached their full height. At 245 meters, Pier 2 becomes the highest bridge pier in the world. But is this record-breaking pillar where it's supposed to be? Amazingly, it's dead on target, to within 2 centimeters. Champagne corks pop. It's time for a major celebration. Against all the odds, they were 1 month ahead of schedule, but the team couldn't afford to relax. The next stage of the project would be the most difficult part of the build. Phase 2 of building the world's tallest bridge involved putting a 2.5-kilometer roadway weighing 36,000 tons on top of the piers, a full 270 meters above the River Tarn. Bridge builders know danger comes with the territory, but working at these heights can be lethal. More than 34 died constructing New York's Brooklyn Bridge. 35 died in 1970 on the Westgate Bridge in Melbourne, Australia. And 1 year later, 13 workers were killed when the Koblenz Bridge in Germany collapsed into the Rhine. With these fatalities in mind, the team decided to fabricate the entire road deck on the safety of solid ground. This meant building it in steel, which in theory would be much safer than lifting vast concrete sections hundreds of meters into position. There's only one problem with this plan. No one had ever put a road deck on piers anything like this height before, let alone over a 2.5-kilometer span. In the end, only one steel manufacturer had the courage to take on this colossal challenge. Eiffel, the steel firm set up by the great French engineer. Eiffel built what was once the tallest bridge in the world, the Garrabie Viaduct in southern France, before getting round to the framing for New York's Statue of Liberty and, of course, his signature tower in Paris. But despite the company's experience, Eiffel's director, Marc Buonamo, knew he was taking a serious risk.
It was a gamble for the company, because if there had been a mistake, if it hadn't worked, it would have been the whole company.
They fabricated the massive sections that would make up the road deck in the company's steel factories. This immense jigsaw puzzle involved manufacturing 2,200 separate sections, weighing up to 90 tons and some of them 22 meters long. Their accuracy is measured with a laser to within a fraction of a millimeter. The huge square tubes are the central spine that should make the deck rigid. The triangular side panels will be welded on either side to create the width for a 4-lane highway. To meet the punishing schedule, Buonamo automated the manufacturing with a 2-headed welding robot and a plasma cutting machine. Each cutting pattern or template is programmed into the computer. Then the machine automatically blazes its way through the steel. The torch reaches a scorching 28,000 degrees centigrade. That's 5 times the temperature of the Earth's inner core. But cutting and welding was the easy part. The hard part was getting these monster sections the hundreds of kilometers from the factories to Millau. The routes had to be planned with precision to avoid major damage. The police coordinated safety and clearances. Even with that level of preparation, some obstacles felt as if they're cutting it just too close for comfort. And this was no one-off event. To build the viaduct took over 2,000 of these extraordinary road convoys. The components arrived at assembly plants set up, one on either side of the valley. Here, the pieces of the massive jigsaw puzzle were welded together to form the 2 halves of the deck. But getting these 2 halves to span the valley on top of the world's tallest bridge piers would be a major challenge. They'd be the first team to put a road deck on a pier taller than an 80-story skyscraper. And pushing bridge building beyond anything attempted before, they planned to slide the entire 2.5-kilometer road deck over in 2 colossal pieces. The bridge's chief engineer, Jean-Marie Kremer, was one of the few people who believed it could be done.
All the engineers who know this method, who were in the know, didn't believe it was possible.
If the team had got their calculations wrong, the entire structure could collapse into the valley.
We found a solution for the construction, which was to launch the bridge from the 2 sides. One part on the Larzac Plateau, one on the Rouge Plateau. And to push them from the 2 sides and to make them come and meet here above the River Tarn.
Smaller bridges use a similar technique. A powerful set of hydraulic rams literally pumps the deck from one side to the other. But Millau would be the longest launch ever attempted over the highest piers in the world, and the results could spell disaster. The deck is so slender, it would bend and collapse if it were pushed out over the 342-meter spans between each pier. The furthest anyone's previously managed is less than half that distance. The first part of the solution was simple. Fit a pylon so its cables support the front of the deck as it goes out over the valley. Then construct temporary steel support towers that halve the spans to a more manageable 171 meters. These steel towers were a construction feat in themselves. The largest, over 170 meters high, is the tallest ever built, and they needed to carry a massive load. 7,000 tons as the leading edge of the deck, together with the first 90-meter pylon slide over. And simply pushing this enormous weight over the top of the vulnerable piers would bring them crashing to the ground. This was the nightmare scenario.
If we'd done a conventional launch, we would have knocked the piers over like the pins in a bowling alley.
Someone needed to reinvent the way this type of bridge is built. And it's Marc Buonamo with Jean-Marie Kremer who came up with the breakthrough. The basic principle can be demonstrated with a heavy box and a wobbly table.
With a normal launch, you knock over the piers. I want to advance the deck over the pier, but if I push the deck from here, I'd knock over the piers, because they're so tall. The idea is to install a launching system on top of the pier, and that way, if I push the deck, it has no effect on the stability of the piers, and the piers won't fall over.
The trick is to use a series of these launching systems to jack up the deck and inch it forward. Each system uses two wedge-shaped blocks under each side of the deck. The upper wedge is pulled forward by a hydraulic ram. It slides up the slope of the lower wedge at the same time, lifting the deck from its supports and advancing it 600 millimeters. The lower wedge then retracts, dropping the deck onto its supports. The upper wedge returns to its original position, and the whole cycle begins again. 4 of these clever devices are placed on each pier, all programmed to work at exactly the same time. The result is that together, they pick up the entire roadway and shunt it forward. But if one fails or gets out of step, it could spell disaster. The force could push the bridge piers apart till they collapse.
When you're up there and you see Millau 300 meters below you, you ask yourself, was this a good idea?
The future of the entire project was now hanging on a prototype, and it had never been tested. It's the morning of February 26, 2003. Do or die day for the world's tallest bridge. Everything is about to be put to the test. The flexibility of the deck, the strength of the temporary piers, and critically, the pioneering hydraulic ram system. Even Buonamo, the man in charge of the launch, had his doubts.
As it had never been done before, I have to tell you, I had fears that it wouldn't work.
The pumps kick in, the pistons start to push, and the deck begins its huge journey across the valley.
The moment I heard the motors start, I put my finger on the deck, and I could feel my finger move.
Every 4 minutes, the deck advanced 600 millimeters across the valley. Surveyors tracked its progress. But it was still a nail-biting time as they watched the unsupported deck crossing the void. Eventually, the deck reached the safety of the first pier. 204 meters down, only 2,256 to go. The launching system seemed to be working as planned. The engineers were feeling optimistic. But as the deck advances into space, it'll become more vulnerable to the wind, which can reach 130 kilometers an hour. Unfortunately, the road deck has the shape of an upside-down airplane wing, and the team's greatest fear is that this wing could simply take off. The engineers kept a close eye on the wind and weather conditions. When they were satisfied there was a 3-day weather window and the wind wouldn't exceed 85 kilometers an hour, they'd give the construction team the go-ahead, and the deck launch could continue. The reason for this precaution is simple. Strong winds can literally tear a bridge apart. In 1940, Washington State built a suspension bridge across the Tacoma Narrows in the US Northwest. It opened with a grand ceremony on July the 1st. But the celebrations were short-lived. The bridge had a major problem: the wind. Girders beneath the deck, designed to make the bridge rigid, actually blocked the wind, causing the roadway to ripple alarmingly. Locals soon dubbed it Galloping Gertie. On the 7th of November, with the wind less than 70 kilometers an hour, the bridge begins to twist violently. At 11 a.m., time runs out for Galloping Gertie. The wind sends the bridge crashing into the river. Wind tunnel testing is now standard procedure as a direct result of Galloping Gertie. For the Malau Bridge, they analyzed the wind in the Tarn Valley over 18 months, then recreated those conditions in the wind tunnel. Wind engineer Olivier Flamand was shocked by the results.
The average wind speed was relatively low, but because there's such strong turbulence, it created very fast peak winds.
The rugged terrain creates serious turbulence at the height of the road deck. Winds peak at 130 kilometers per hour. That's hurricane force. They tested every aspect of the bridge to analyze the risks: piers, pylons, and critically the deck. But it's not just the aerodynamics of the finished bridge. They needed to find out how it would behave when it was most at risk, during the launching of the deck. Olivier and his team reached a chilling conclusion. The winds they've measured are strong enough to blow the unsecured deck off its supports and send it crashing hundreds of feet to the valley floor. And then the nightmare began. On the 22nd of August 2003, 6 months into the deck launch, one of the launch systems failed, leaving the deck hanging in the wind. To make matters worse, the weathermen were predicting storms. So far, these massive pumping machines had worked perfectly. But the fact is they were prototypes, and due to the frantic schedule, they'd never been tested. The problem was that the non-stick Teflon between the sliding surfaces had ripped, and the friction generated was too much for the hydraulic rams to push against. Unfortunately, no one had planned on replacing parts of this monster machine mid-launch on the top of a massive concrete pillar. This was very bad news for the man who staked his reputation on this system.
It was maximum stress, like poison in your mouth. You don't forget that.
Re-examining their calculations, they realized the cause of the problem. They'd underestimated the forces between sliding surfaces, but they wouldn't be able to repair it without the necessary spare parts. The clock was ticking, and Marc Buonamo needed a solution fast.
When Apollo 13 came back with that incident, the NASA engineers requested they did the inventory of everything there was on board to know how to fix it.
The Malau team did an inventory. They realized that the other launching machines, not yet being used, could be stripped to provide the new Teflon surfaces they needed. Working all through the night, the team extended the access platform. This allowed them to take out the 5-meter-long, 2-ton steel wedges, replace the Teflon, and reassemble the launching machine. By 8 a.m. the next morning, it was ready to resume the launch. The rest of the week, the predicted storms arrived, and another set of launching machines wore out. So when the deck finally made it to the safety of the next pier, the team breathed a major sigh of relief.
You don't forget that. I won't forget that for 4 hours I was really scared.
The two decks continued their journey across the valley, day after day, week after week for a full 14 months. They approached each other, millimeter by millimeter. By May 2004, they'd reached a critical phase. From the northern end, the shorter deck had traveled 717 meters into space to reach its final resting place. From the south, the longer deck extended over 1.5 kilometers. Only the section over the river, the one point where it was impossible to erect a temporary pier, divided them. But would they meet as planned? If they've got their calculations wrong, they'll have built the biggest white elephant in Europe. Even the man behind the whole project had his doubts.
I was not convinced at all that the two parts of the deck could meet exactly with a perfect geometry.
The odds were against them. Calculating such a feat so precisely is a Herculean task. Firstly, the two starting points on the northern and southern slopes of the valley are at different heights. Secondly, the bridge has a subtle curve to it. As a result, each steel panel which makes up the road deck had to be cut and welded with extreme precision. It would be an engineering triumph if they got these two sloping curved decks to meet as required. The team checked the weather reports. With the wind inside safety limits, they gave the go-ahead for the final push. The rams began to drive the deck's leading edge off the safety of Pier 3 towards its destination. At this point, a total of 21 launching systems needed to move at exactly the same moment to avoid disaster. If anything were to go wrong now, the man responsible would be Marc Buonamo.
Everyone asked me, how can you be sure that it will go straight? So to be sure that they were going to the right place, I had a GPS put on the front, so I could see the gap between the theoretical and the real position.
Over the next 2 days and nights, the deck advances 600 millimeters at a time towards its final resting place. The world's media are watching the critical meeting of the decks, and to add to the pressure, the French Prime Minister is due to drop in to celebrate the event. The deck pushes forward, now with only centimeters separating the two sections. A magnum of champagne is hung between them to mark the moment. At last, union. The two massive steel decks have traveled high over this valley, a total of 2.5 kilometers, and when they check, they're aligned to within 1 centimeter. That's accurate to within 99.9999%. All the measuring, all the calculations have paid off. They've nailed it.
The meeting of the decks was a special moment.
News reports traveled round the world, and in Salzburg, Austria, they reached Felix Baumgartner, aka Felix the Conqueror. Felix has made a career base jumping from some of the tallest structures on the planet, and within 24 hours, he'd driven to Malau and was calculating the logistics for the jump. Factoring in his two main aims, to avoid arrest and death. Baumgartner waited for darkness before arriving on site. He found his way to the base of Pier 2, then climbed an access ladder the full 245 meters to the top. He entered the steel road deck and found a place to hide until daybreak. He had to remain concealed until the sun was high enough for his cameramen to record his world record attempt. At 7 a.m. the following morning, Felix the Conqueror emerged. He took a cool backward flip off the tallest bridge in the world and entered the record books.
The tallest bridge in the world, 250 meters.
I did it.
And having evaded death, he made sure he's not caught by the police. The decks have been joined, and the team have reached the final phase of the project. But there was still a race to meet the schedule, and their problems weren't over yet. Everyone could see the dramatic undulations in the flexible steel deck. Even some hardened bridge builders wondered about its structural integrity.
It was a huge surprise for everyone. All the engineers said, we knew steel was flexible, but not that flexible.
The team were relying on the pylons and cables to pull the deck straight. Each massive pylon is 90 meters high and weighs 700 tons, the equivalent of 85 London buses. Placing them in position on the slender deck, high above the valley floor, would go beyond anything ever attempted. Once again, Marc Buonamo had a plan.
You know, the first people to make vertical pylons were the Egyptians.
Buonamo adapted a technique used in ancient Egypt to erect obelisks in the sands. On top of the road deck, the team put up two enormous steel towers, both of them secured by cables and equipped with a hydraulic system capable of raising 1,000 tons. The 700-ton pylon is then lifted by the hydraulics. As it rises, it pivots little by little until it's vertical. It's then lowered safely onto its anchorage point. Buonamo's 4,000-year-old technique worked to perfection. With all 7 pylons in place, the team could attach the cable stays that would straighten the rippling deck and give it the strength to cope with full traffic loads. They hoped. The weight of the roadway is now over 40,000 tons, the equivalent of a cruise ship, and the 154 cable stays should prevent it from sagging or collapsing. The strongest stays are made up of 91 individual steel strands and have a braking strength of 25,000 tons, strong enough to hold back 25 jumbo jets, all at full throttle. As the cable stays at tension, true to plan, the ripples in the road deck are pulled straight. Over the 2.5-kilometer deck, the ripples are now no larger than the size of a thumb. They're finally on the home straight. The road surface goes on, adding a further 10,000 tons to the load. That's like driving 153 battle tanks onto the deck. But before it could open to the public, the team needed to know the bridge is safe. It would have to pass one crucial test. After 3 years, the construction team building France's Millau Viaduct, the world's tallest bridge, are about to find out if they got their calculations right. On a single-span cable stay bridge like the Normandy Bridge, a large load on the main section is no problem because the cables are attached to solid ground and can't give. On the Millau Viaduct, with its 8 spans, the cables are attached to the deck of the adjacent sections. A load on one section will cause it to drop, pulling the stays down. As the pylons lean in, the matching stays are pulled upwards, lifting the neighboring decks and causing a dangerous rippling effect. It's right now the team put their bridge to the test. These 28 trucks have a combined weight of over 900 tons. They are now positioned in the critical point, mid-span. The engineers hold their breath. Measurements are taken. The span bends just 26 centimeters. This is a triumph for the engineers. The bridge was designed to cope with more than double that. 4 weeks later, on December the 14th, 2004, President Jacques Chirac officially opened the Millau Bridge. A proud moment for the whole of France. Just over 3 years of construction have produced the tallest bridge in the world, designed to last at least 120 years. And against the odds, the project manager even brought the job in on time. But that's not what he's most proud about.
What I remember, because on construction sites there are often accidents, is that we had no serious accidents, nothing more than a minor injury.
As soon as it opened to the public, the bridge was an instant success. But the real test isn't till its first summer, and the French all take their annual vacation. No one ever expected anything like this. Numbers peaked at more than 50,000 vehicles a day. At over $7 per car, that's great news for the construction company, who are clawing back their $478 million investment in the project. This was an epic bridge to build, but it's just as epic to maintain. Thierry and Frank are assigned to P2, the world's tallest bridge pier. This structure is no solid concrete block. It's a series of vast hollow spaces. Their job today is to test the communication system and electric circuits on each of the 7 structural floors. This involves a 343-meter climb, going hand over hand up a ladder for the rest of the day. By dusk, when Thierry finally reaches the summit of the pylon, he may be exhausted, but there is a payoff.
You get a fantastic view from here, a 360-degree panorama.
The tallest bridge in the world has become an icon. But this is creating problems no one had ever imagined. Locals have been taking over the bridge as a platform to get media attention for their causes. This crowd was hoping that driving sheep over this freeway in the sky would help them get more farming subsidies. Jose's job is to prevent this kind of incident from creating a danger, and on this bridge, the incidents keep on happening. An alarm triggered by a motion detection system means there's a stopped vehicle on the bridge. Immediately, Jose dispatches a colleague to deal with the situation. The last thing anyone wants is a multi-car pile-up on a 2.5-kilometer bridge, quarter of a kilometer in the sky. Jose zooms in his camera to reveal the man has left his car and is sitting dangerously on the crash barrier. The driver's probably only broken down, but already one man who stopped climbed over the wind barrier and jumped to his death. Bruno intervenes. Thankfully, it's no more than an irresponsible photographer who's sent on his way. You could say the Malau Bridge is a victim of its own success. It's definitely become a major tourist destination. 700,000 visitors in the first 9 months. Fortunately, most of them wait till they're off the bridge to take their photos.
It's magnificent.
I came 600 kilometers today to see the Malau Viaduct.
There's only one thing to say. It's extraordinary.
They're drawn because it's a world-beating structure, but also because it's incredibly beautiful, delicate, and minimal. Not what you'd expect from a structure that's nearly a third taller than any other bridge on the planet. And architect Lord Norman Foster's achieved his aim to give the driver the sensation of soaring.
As you leave these plateaus, you do fly. You fly across this bridge. Literally, you are above the clouds.
And the result certainly pleases the man who dreamt it all up.
To see erected this bridge, which I imagine 15 years ago, it's something magic.
This is the longest pure cable stay bridge in the world, the tallest roadway in the world, and of course at 343 meters, it is the tallest bridge ever constructed.